Hi students, in this video I'm going to be talking to you about inclined planes and how to solve them. So an inclined plane is one where if you just consider the horizontal surface, say a floor or anything that's perfectly horizontal, and you put a plank of wood on that, and then if you were to raise that plank of wood, you'll end up having it at an incline, which means it's at an angle to the horizontal. And for now I'm going to call that angle theta. Now if I then put, say, an object on that inclined plane, the forces acting on that object are no longer sort of the same as when you consider another case. If I draw down here, if I just draw that box on top of a flat surface. So the forces acting on this flat surface we know. We know that there's a weight force due to gravity that's acting down. We can call that W or mg. And it has an equal and opposite reaction force due to Newton's third law, which is known as the normal force, and that acts perpendicular to that surface. Now where that becomes a problem is if this surface here is not perfectly flat, and that's when we come across this inclined plane. So the force due to gravity is still going to be the same. It's acting downwards, and that's all well and good. Now the reaction force from the surface needs to act perpendicular to the plane, so it sort of has to act in this direction. In reality, what it's doing is it's reacting to the perpendicular component of the weight force. So remember, the force that the plane is pushing out on this box is going to be reacting to this force here. And this force here is the perpendicular component of the weight or the gravity force. And there's also another component, which is this one here. So remember, I'm just splitting it up into its two orthogonal components. One is acting into the plane, and one is acting along the plane. So since our particular normal vector is going to be reacting to this, that would mean, if I just reverse all this up, so the reaction force is going to be equal and opposite to that component vector. So it's going to come out and sort of look like this. Now importantly, the length of this normal vector is going to be a little bit less than the full magnitude of the weight, right? And what I've drawn here are the only two forces that are acting on this box. So there's a weight force acting down, and there's a normal force that's acting perpendicular to the surface. Now if I was to draw this as a vector diagram, I would have the weight force acting down, followed by the normal force acting up like so, and it should be in line with, so that we have this sort of gap here, and the direction of this gap should be the direction of the slope. Now what happens here depends on the scenario. So this, if there was another force acting, we could say that maybe friction is acting like this. So we have the weight force like that, we have the normal force, and we have the frictional force, and then by ending up at the same spot we can say that that box is not moving. However, if there was no frictional force, and we just said there are only two, just like in this scenario here, there are actually only two forces acting on it, that would mean that we end up with a resultant force that is acting down the slope. And that resultant force means that box will slide down that slope, it'll accelerate down the slope. So another thing that you might want to consider, if I convert my diagram here on the left, instead of having a free body diagram, if I draw this as a vector diagram, I'll make it light blue just for fun. And so I draw the weight vector coming down, and then I draw the normal vector coming up, head to tail. Now, regardless of what happens here, I'm just going to ignore this for now. In this particular case, we say that there's going to be a resultant vector. So, if I wanted to, I could just put this here and say R. But that's not the point. What I wanted to show you is that if you look here at this theta, and we can see that there's a right angle here and there's a right angle here, which means this angle here must be whatever 90 degrees take this theta is. So I'm going to call it phi because it's irrelevant. But what that means is this value here, that angle, is therefore going to be theta. And if I then substitute that over here, that means in my vector triangle, this angle here is going to be theta. Theta being the angle of the slope. So whenever we do an inclined plane problem, we draw our vectors in a way that we've got an angle and three different sides of that triangle. So now let's put this into practice. So in this question, you've got a brick, it tells you the mass of it, and it's on an inclined plane. Now it's telling you that it's a rough surface, which means you're going to be having friction. So what I'll do is I'll just draw that in. Now what I'm going to do in here is I'm not going to draw the free body diagram. Instead, on top of this diagram, I'm actually just going to draw the vector diagram. So there's my brick, and I'm going to draw the vector going down. Notice that the length of the vectors doesn't really matter. I have this downward force, which is mg, and then there's going to be a normal force that comes out to here. And then in this particular case, it tells me that friction is preventing it from sliding down the plane, which means there must be a third force acting here, and that's going to be friction. And my angle here is the same as this angle here, which is 15 degrees. So now I can just do some maths, right? So I know that sine 15 is going to be equal to the opposite over adjacent, so the friction divided by mg. So friction is going to be equal to mg sine 15, which is going to be equal to, in this case, 3 times 9.8 times sine 15, which is 7.61 newtons. And in this case, it's acting up the slope. So don't forget to give a direction because it is a vector. And there you go. Now, another version of the question that you might get is this one that we've got in Pearson, where you have a skier and it's an icy slope and it has an incline, all that stuff. And it's asking a few specific questions. So this is sort of scaffolding it a little bit more for you. So let's just draw the scenario first. So again, we've got a slope and you've been given the angle here as 30 degrees, and my skier is going to be a green box, surprise surprise, and I'm going to draw in the gravitational force first, right? So there we go, there's your weight, mg. Now this particular question scaffolds things much more nicely for you, but in that way it might actually cause some issues. So it's asking for the component of the weight force that's perpendicular to the incline. So this is our weight force here. And I can say that that is made up of two orthogonal components. Here is one orthogonal component, and this is running perpendicular. And then you've got another orthogonal component acting like this, and that one's acting parallel to that slope. So it's asking for the lengths of the perpendicular and the parallel parts of the slope first. So to solve for the length of the perpendicular and the parallel lengths, what you need to do is find out an angle in here. Now it's a little bit different to the other scenarios. Of course, you know that from the previous question, that the length of this parallel component is going to be mg sine theta. So you can take that shortcut right now and you can put in 100 times 9.8 times sine 30 and you will get the parallel. And would you believe it, the perpendicular one would just be cos of that 30 degrees. But let's sort of derive it, normally. This is 30 degrees and it comes across, it cuts in, and that would make this angle here three similar triangles. Since this one's going to be 60, this one therefore must be 30 degrees here. So if I were to do it that way, I can answer A by saying that I'll do the perpendicular one first. Okay, so perpendicular is going to be the adjacent over hypotenuse. Cos of 30 is going to be equal to perpendicular component divided by mg. Therefore, my perpendicular component is going to be equal to mg cos 30. In this case, it's 980, or 9.8 times 100, cos 30. And I will get 848.7, so 849 newtons. And for part B, it's the parallel component, and it's just going to be the other side, so it'll just be mg sine 30, which is going to be equal to, 490 newtons. And that's all great. So it's scaffolded those things for us. And what it says here is determine the acceleration of the skier down the slope. So if we relook at that diagram, if I was to sort of draw what's happening, we've got a downward force acting, which is your weight force. We've got a normal force coming out from the slope. And then what you have left over is this resultant force. So in this case, there's no friction. So you have this resultant force. And this angle here is 30 degrees. So this resultant force, we should be able to identify by now, hopefully, that this resultant force is the same as this parallel force. So that would mean that the force itself, the resultant force, is going to be equal to 490 newtons. So since I know that, to find the resultant acceleration, that's going to be that force divided by its mass. So it's going to be equal to 490 divided by 100, or in this case 4.9 meters per second squared. Now what's really interesting is you could answer that part C without having any of the other information nor the mass. So let me show you what I'm talking about. So if I was to draw my triangle again, instead of saying weight like I have here, I'm going to do it in terms of acceleration. So I'm going to say G. Instead of mg, I'm going to say G. So the acceleration acting downwards is 9.8. There is another acceleration acting this way, and that acceleration is your net acceleration, right? And here is 30 degrees. So I could say, therefore, the net is going to be equal to G sine 30. So the net acceleration is going to be equal to 9.8 times sine 30, which is going to be equal to, would you believe it, 4.9 meters per second squared. And there we go. So I think those problems should be a good, well-rounded way of introducing you to inclined planes. It doesn't get much more difficult than this at all. Maybe they might complicate things by having a little different forces acting instead of just one frictional force. But other than that, it's pretty straightforward. So I hope you find it useful. Thanks.